Hello and welcome to another session in physics. In this session we'll be looking at the topic electric measurement. But before that, let's review the previous lesson. Welcome back. Like I said, we'll be looking at electric measurement, and one important aspect when it comes to electric measurement is resistivity and conductivity. Now, let me make it clear that resistivity is quite different from resistance. Resistance simply refers to the opposition offered to the flow of electric current. It is quite different from resistivity. It's different from resistivity. So what is resistivity? Resistivity simply refers to the cross-sectional unit resistance per area of a conductor. The cross-sectional unit resistance per area of a conductor. You see from the slide here that the resistance of a wire maintained at a constant temperature is related to its length and its cross-sectional area by the expression R equal to, this is rho, Greek alphabet called rho, it is not B, rho times L over A, where L is the length and A is the cross-sectional area. Alright, so this rho is a constant of proportionality that is known as the resistivity of the material. Therefore, when we make it the subject of the equation, we're going to have the resistance multiplied by the length divided by the cross-sectional area. The cross-sectional area can be found by multiplying pi with the radius squared, or we can have pi d squared over 4s, where r is the radius of the conductor and the diameter of the conductor is d. Now let's talk about electrical resistivity. The resistance of a unit length of material of unit cross-sectional area is what we call the resistivity of electricity. The resistance per unit area of a material is what we call the resistivity of that material. Remember that resistance is measured in ohms, area is measured in meter squared, and length is measured in meter. And the unit of resistivity is ohm meter, like ohm meter, resistance times length. The resistance of a material, like I already said, is the ability of that material to oppose the flow of electric current through it. So you would notice that the greater the resistivity of a wire, the poorer it is as an electric conductor. Because when its resistivity is very great, it simply means that its ability to conduct electricity is highly inhibited. That is why we have conductivity used to specify the current carrying ability of a material, or the amount of current that a material can allow to flow through it. Conductivity is the opposite of resistivity. So the greater the conductivity of a material, the more easily electric current can flow through that material. Hence, materials with high conductivity will have low resistivity. On the other hand, materials with low conductivity will have high resistivity. So they are the inverse of each other. Conductivity is described using this Greek alphabet called sigma. This is small letter sigma in Greek alphabet. This is capital letter sigma, which is used to show summation. So conductivity is represented using this, and it is the reciprocal of resistivity. Now, like we've already said, conductivity is the measure of the extent to which a material will allow current to flow easily through it when a potential difference is applied at a specified temperature. Like we've already said countless times, it is the reciprocal of resistivity. Let's talk about the internal resistor of a cell at this point. In the absence of an external conductor, a chemical cell develops a potential difference, E, which is what we call the electromotive force, the EMF of that cell. The electrolyte inside the cell offers a certain amount of resistance when its terminals are connected and current flows through it. This is what we call internal resistance of that cell. The potential difference required to drive a current through a cell is known as IR. IR is current times resistance, which gives us lost BD. Remember that from Ohm's law that potential difference is equal to IR, current times resistance. Alright, so we have I, current, equal to the EMF of the cell over capital letter R over plus small letter r. Capital letter R is external resistance, small letter r is internal resistance of the cell. At any point in time, you can make either of the quantities the subject of the formula. Now let's look at galvanometer conversions, still under measurement in electricity. We have a galvanometer, which is an instrument used to measure very small quantity of electricity. Another instrument we use to measure electricity or electric current is an ammeter. But a galvanometer helps to show very small, infinitesimally small amounts of current. Now, there are times when we may need to measure big amounts of current, but we don't have an ammeter there, and all we have with us is a galvanometer. And this galvanometer, for it to be able to measure a huge amounts of current, we need to convert it to an ammeter. When a galvanometer has been converted to an ammeter, we call it a shunt. Actually, a shunt is an instrument we use to connect with the galvanometer so that it can be able to measure big amounts of current. This shunt is called a resistor. It is a low resistance wire, and it is connected in parallel with the galvanometer to allow quantity of current to pass through it. Alright, now when we convert a galvanometer to a voltmeter, we can actually use it to measure potential difference or voltage. We do this by connecting it in series with a multiplier. A multiplier is a high resistor, a high resistance material, a resistor that has a very high value. We connect it in series with the multiplier and we use it to measure voltage. Now let's see how we can measure resistances. We have so many methods of measuring resistances. We can use the voltmeter ammeter method. We can use a device called the Wheatstone bridge or the meter bridge, or even a potentiometer. We're going to look at some of these devices in the following slides. What you see here on your screen is called a Wheatstone bridge. The Wheatstone bridge is an instrument we use in getting accurate resistance. Under normal circumstances, it consists of about 4 resistors, namely R1, R2, R3, and R4, and they are connected side by side together to form a closed circuit. So when we vary the resistance, a certain stage is reached where no current can now flow through the galvanometer at the center, indicating 0. So these are the calculations we have to make for us to arrive at the value that we want to get the potential difference right where we want it to be. Now this instrument you see right here is a potentiometer. A potentiometer, we have the EMF in the first column, the length of the first column, the EMF in the second, and the length of the second column. Now, what are the advantages of a potentiometer over a voltmeter? Advantages of a potentiometer over a voltmeter is that a potentiometer does not draw current from the circuit at a balance point due to its internal resistance. Secondly, a potentiometer has no zero scale error. And thirdly, it gives an accurate reading for potential difference than the voltmeter. I'd like to point out something here, that if we want to take a reading about a potentiometer, we can always equate the secondary EMF with the secondary length and the primary EMF with the primary length. And at any point in time, you can take proportions and then we can actually use them for readings. I'd advise you to watch videos of some practicals online. You can ask your physical teachers for assistance on how to use this instrument. Thank you so very much for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your screen.